welcome to CNI seminar series. Today we have Professor Lalitha Vadlamani from IIIT Hyderabad with us. She will talk on efficient repair of Reed-Solomon codes and Tamo-Barg codes. Good evening. Lalitha Vadlamani received her BE degree in Today we have Professor Lalitha Vadlamani from IIIT Hyderabad in 2003. She will talk on efficient repair of Reed-Solomon codes and Science Bangalore codes. In 2005 and Lalitha Vadlamani received her BE degree in Today we have Professor Lalitha Vadlamani from IIIT Hyderabad. Signal processing and communication talk on efficient repair of Reed-Solomon codes and Science. She is currently an associate professor. Lalitha Vadlamani received her BE degree in Today we have Professor Lalitha Vadlamani from IIIT Hyderabad. Signal processing and communication talk on efficient repair of Reed-Solomon codes and Science. She is currently an associate professor. She is a recipient of Professor received her BE degree in Today we have Professor Lalitha Vadlamani scholarship for the year 2011. She is currently serving as the newsletter editor of the IEEE Information Theory Society. Welcome, Professor.
Thank you for the introduction and thanks for inviting me to give a talk in the CNI seminar series. I think they asked me way back in September maybe, and I said November may be a good time. Okay, so I'm going to talk about efficient repair of Reed-Solomon and Tamo-Barg codes. See, these are both codes used in distributed storage, and I give my initial motivation kind of for distributed storage. Maybe those who have heard me before, that part might be slightly repetitive, but soon we'll get to new things. So this is a system that we have in mind. It's a distributed storage system, and the way things are stored here is using what is called erasure coding. So let's say there is a file, and it is divided into like blocks, right? So ABC are, let's say, blocks of size 64 MB or any other size, and these have to be like stored in nodes. So this is what happens in, let's say, a Facebook system or so. So here I have just shown 5 nodes, and I mean, just to add redundancy to the the data that you want to store, so that any node failures can be tolerated. So here we are adding some redundant blocks. So for ABC we are adding 2 more blocks which are redundant. One is A plus B plus C, and the other is A plus 2B plus 3C. So when I write this plus, it is like it's these operations are happening over a finite field. If you want, you can think of it at bit level, byte level, or whatever. So that also is okay. So the thing is that these blocks now are stored in, let's say, 5 nodes. Okay. The kind of resiliency that we are getting is that if any 2 blocks are lost, still we have the data, right? Because you can recover ABC by solving a system of linear equations, right? So this is like using a 5-3 code to store the data in a distributed storage system, right? So this kind of coding is very fast kind of replacing the replication based schemes, because replication involves a lot of overhead for the same amount of resiliency to failures that we want, but whereas erasure coding is like very highly storage efficient. So that is the reason erasure coding is being considered even like by, let's say, Microsoft and Facebook, because they know that over time, you can't keep replicating all the time, right? Okay. So there are 2 kinds of failures in a distributed storage system. First, the node. So in the previous slide, I have shown 5 nodes. So one node is what is called a failure domain for us. So in a distributed storage system, failures can happen at different levels. So like a sector can fail, a disk can fail, a node can fail. And for the purposes of this talk, we will just think nodes are the ones which are failure domain, which means a node fails, right? And for us, the way to think about it is that each block, encoded block, I'm going to place them in different storage, different failure domains. Okay. The reason is because if I, let's say, place AB in the same, so 2 blocks in the same node, then I know that if node 1 fails, then both the blocks are lost anyway. So that, for the same probability, I'm losing more data. It doesn't make sense, right? So we want to place all these blocks in different failure domains, which means different nodes, right? And there are two kinds of failures which can happen in a distributed storage system. One is temporary failures and the other is permanent failures. So the permanent failures are very, very rare, okay, but it can be like a catastrophic kind of failure where, you know, one node failed, before you repair that one, the second node failed, and let's say a series of 3 nodes failed even before you could repair the first one, let's say, right? So those are like permanent failures, and that kind of happen very rarely. And the second kind of failures are temporary failures, and these failures happen much more often. Okay? And these could be like some reasons are like let's say there is a power outage and the node is temporarily unavailable, right? So you know that the data is there, but for the purpose of you know, the client, whoever is requesting for the data is not available, right? So those are kind of temporary failures. So maybe the system is slow because there is a software upgrade running on the node, or there is a power outage. So these are like some 2 examples of temporary failures, right? And for temporary failures, you know that the node is, I mean, the data is there, but it is just temporarily unavailable, okay? So which means that you need not have to recover the contents of the whole node. So suppose somebody is requesting for block A, okay, because in that node there can be like 1000 blocks corresponding to different users stored, right? But somebody is just asking for this block A, and the system has, and node has undergone a temporary failure. So we want to make sure that somehow we repair that node A, or rather recover that node A quickly and service the request, okay? So that kind of brings us to the problem of, okay, so this one, which is called single node failures in a distributed storage system. So which means that typically if you look at, you know, across days and across machines, many times it is only nodes. So by the way, yeah, so the number of failures which are unavailable for greater than 15 minutes, but most are like, you know, in a very big system, there are some nodes which are unavailable. But then if you have these 5 blocks, okay, most likely one block is what is in those 40 machines which has failed perhaps, right? So which means that you have to consider only single node failures mostly, okay, single node or very small number of node failures. So that's what, and in this talk we will talk about single node in particular, and also like I will generalize it to a few nodes failures perhaps, right? So this is statistic from a, you know, a measurement thing which was done on a Facebook warehouse cluster, okay? So just going to a little more abstraction. So erasure code is what I have told you, which was a 5,3 kind of a code, and in general there are things called MDS codes which are used for erasure coding. So these are maximum distance separable codes, and because they have good minimum distance in the sense that they meet what is called the singleton bound. So which means that for, you know, for given n and k, that is the best minimum distance that you can get, right? And minimum distance is also related to the number of erasures you can tolerate, okay? So yeah, I'm kind of slightly skipping the model, but the model in these storage systems is what is called erasures. And erasure model is different from an error model in the sense that in erasures you know which blocks are missing, okay, versus in errors in general, I mean, you know that something has been corrupted and you don't know exactly which one was corrupted, okay? So that is the difference, and we will just deal with erasures, right? So if a code has, you know, if an n comma k code has a minimum distance d, then we can tolerate kind of d minus 1 erasures, okay? So if d is large, the number of erasures that we can tolerate is large, right? And that is why MDS codes are useful. And one code which is used in Facebook in cold storage, again, it was there in Hadoop for some time. It moved to a kind of a branch thread, I would say. So it is a 1410 kind of an MDS code, okay? So where there are 10 message symbols or blocks, okay? And there are 4 parities which are added to it, so it becomes a 14,10 MDS code, and the storage overhead for that is 1.4x, okay? So this is like just to give you some idea about numbers. In particular, actually, currently the codes, the length of codes that I use may be, in general less than 100, right? So because you don't want to use very long codes that creates a lot of interdependency. Maybe you still want to keep your code length somewhat short. Okay, so but of course that will scale based on your system scaling. But for the current systems, maybe it's still okay to have codes whose length is less than 100 for sure. Right. So for this kind of problem, so in the case of temporary failure, we are saying we want to tackle single node failures. Okay. And in the single node failure problem itself is called the repair problem. Okay. So what are the metrics of interest for repair? We want to minimize the storage overhead, how much extra we are storing, right? And for the case of single node failures, we also want to minimize the repair bandwidth. Okay, so here actually there are two metrics. Okay, so one is called the repair bandwidth, so which means that suppose one node failed. Okay, and then I am looking at how much MB of data that I am downloading in order to repair this block, right? So that is called the repair bandwidth. Versus there is another metric called repair degree, okay, so which is the second one, where one block has failed and you are looking at how many other nodes that I have to contact to be able to recover this one. Okay, so both those classes of codes are well studied in literature. One class is called regenerating codes and the other is called locally repairable codes. Okay, and a lot of work in both these things has happened even from IIIT, like okay. And I started working on like LRCs and all even during my PhD. Like middle of my PhD was when some papers in LRC, the first papers in LRC also have come. Okay, so these are the metrics of interest. And in this talk we'll be interested mostly in repair bandwidth and in the second half also somewhat in repair degree. Okay, so what we want to do is, so the route that both those codes have taken is that you define the problem and then you say that for solving that problem, derive the fundamental limits, design codes, etc. Okay, so that is the way in which regenerating codes and LRCs where the literature has progressed, let's say. So there is, but Reed-Solomon codes have always been there in literature. Okay, in the sense that they were always there for storage, right? Including like let's say disks and so on. So Reed-Solomon codes are very well known MDS codes for storage. So then the question came up after this regenerating codes and LRCs, can we repair the Reed-Solomon codes themselves? Okay, means can we make the Reed-Solomon codes have better single node failure repair property? Right? What does it take to do that? Right? So in regenerating codes, the main trick which is used is called vectorization. Okay, so which means that I don't know if I write how it will be, but anyway. Okay, so what happens is that, so the way I have shown you the code before is that I had this 10 message symbols and then I had 4 parities, right? So this is in some sense assuming that each of these symbols is some symbol over a Q, let's say, right? So this is termed, let's say, a scalar code. Okay? Because each node is storing one symbol of that field, right? So the main thing in regenerating codes which gave the advantage for the case of single node repair is what is called vectorization. Okay? So what it does is that, so instead of storing one symbol, I'll store, let's say, 2 symbols or some alpha symbols in a node. Okay, and so there is a way to look at vectorization of the scalar codes itself. I will take 10 symbols from each of these, and as if I am layering it, I can view that as that too, right? But the difference between that and a code like this is that here So suppose if I am stacking, you know, some 1 dash, 10 dash, and I have P1 dash, etc., right? So there is no connection between this code, I mean the symbols here and here, right? So but in a regenerating code, suppose if I have, so this is 14 plus 14, 28 symbols, all the 28 symbols are part of one code. Okay. So what is the key trick? The key trick is vectorization, and which gave the advantage with respect to single node repair. Okay. So now in the case of Reed-Solomon codes, okay, Reed-Solomon codes by themselves are scalar codes. Okay, I'll describe what a Reed-Solomon codes is. By themselves they are scalar codes. Okay, but suppose if I want to somehow vectorize a Reed-Solomon code, okay, and get the advantage for the case of single node repair. So that is what we want to do. Okay, so for the what is the advantage is that so whenever you want to recover this, I can download parts of other symbols, right, or even linear combinations of those symbols. So when it was a scalar code, you either had to download that symbol or not, right? So the advantage of vectorization is that it will allow you to do operations between the symbols stored in that node and send a linear combination of that. So that is the trick that we want to do for Reed-Solomon codes also, to make them efficient with respect to single node repair. Okay. So just a quick thing about Reed-Solomon codes. So let's say I have a message vector of length k over a finite field q. You form the message polynomial, which is f of x, which is a sigma I equals 0 to k minus 1 mi x to the I. So that is a message polynomial, and you're going to, you'll evaluate this message polynomial at n points, right, n distinct points, and the code word is that, the code word is evaluating the evaluation of this at n distinct points, so it is f of alpha 1 to f of alpha n. Okay. So this node can tolerate n minus k erasures. So the reason is because any polynomial of degree k, right, a degree k minus 1, I require only k evaluations of that to determine that uniquely, right. So which means that I will be able to find out my message polynomial, and then the other n minus k whichever have been erased, I just substitute the values of evaluation points there and get those values, I mean those symbols, right. So that's a quick way to say that this code can tolerate n minus k erasures, and in particular minimum distance is n minus k plus 1 more than the number of erasures that you can tolerate. So that is Reed-Solomon codes. Okay. And the naive repair scheme, which, you know, before let's say even 2014, what people were always thinking is that we'll do just naive repair. So which means that if a symbol, even if one symbol is lost, okay, so you still download, I mean in the sense you access k nodes, download k evaluations, find out the message polynomial, and then recover this f of alpha star which was erased, right. And that is the only method which was known before, let's say 2014. Okay. So the first time, the first paper which actually did better using vectorization, let's say, was by Shanmugam et al. It's called a repair framework for scalar MDS code. So they did it for, you know, they gave some framework and showed that for particular cases of codes, like, so there was a 5,3 code and 6,4 code. So for these things, you can get advantage as compared to just doing the naive repair. Okay, some advantage. So when I say repair bandwidth advantage, how is it? So there is some vector operation which is going on here, and I can show you what that vector operation is and why it is important. Okay, so what you do is that I have my Reed-Solomon code. So let's say there was they are talking about 5.3 or 6.4 Reed-Solomon code, right? So I have these points. So f of alpha 1 to f of alpha 5, right? And this is a k equal to 3 code, right? So I'm looking at all polynomials of degree 2, right? And then I'm evaluating them at alpha 1 to alpha 5, okay? So now these things, so let's say it's over some finite field fq. Okay? So if you want a Reed-Solomon code, let's say it's over f8, okay? A finite field of size 8, okay? So now let's let's say f of alpha 1 is the one which is erased, correct? So what you are thinking of is that I am going to view each of these code symbol as if it were a vector of length 3 over f2, okay? So this is, so f8, so there is an f2 sitting inside f8, and there is a way to view symbols of f8 as if they were vectors over f2, because you know, an extension field is a vector space over the base field, right? So these are all, you can view them as if they were vectors over f2, right? So earlier what I was doing, I had to do 3 times 3 symbols, which was 9 symbols, okay, 9 bits, to be able to recover f of alpha 1, okay? If I view them as vectors and do some linear combinations and transfer, right, if I am able to do better than the 9 symbols, then I have gained, right? So that is what they have done, okay? So for specific examples, they have shown that, in particular these codes, okay, they have shown that you can do some linear combinations by viewing the symbols as if they were vectors over the base field, okay, and using that you can get advantage in terms of repairing a single node or a single symbol, right? Okay, but again, so this was, the framework was such that they showed advantage for particular cases, right? It's not a general framework. So then later came the Guruswami and Wootters. Yes, that is correct. Yeah. So any node among the 5, whatever is the length of the code, yes, that's correct. Yeah. So then, so there was a paper by Guruswami and Wootters. I think the first paper came in 2015. Maybe the later journal version came much later. Where what they are doing is kind of giving a very general framework, okay, in which you can do this, okay, and for that we require a few concepts related to, and this talk actually is quite heavy on finite fields, okay. I don't know how far I can go, but it's quite heavy on finite fields. So okay, anyway, the first fact which will be useful to see what is their repair scheme is that dual of a Reed-Solomon code is a Reed-Solomon code, but it is generalized, okay. So when we say generalized, what is happening is that, so earlier I was just having this f of alpha 1 to f of alpha n. Now I have, you know, v1 to vn, which are multiplying this f of alpha 1 to f of alpha n, okay. And these are some non-zero elements in the field. So you cannot show, I mean, it is in general not true that dual of a Reed-Solomon code is Reed-Solomon code. It is a generalized Reed-Solomon code. Okay? So these can be non-trivial elements. They all need not be 1 for the dual. Okay? But for all our calculations, this v1 to vn do not matter. Means in the sense they exist, and that's all that we care about. Actually, what their values are, etc., does not matter. Okay. So, but because we are considering an NK Reed-Solomon code, and again it's an MDS code, so the dual has length n, dimension n minus k, right, and d minus k plus 1. And it's a Reed-Solomon code, so all the f's are still polynomial evaluations only. Okay, polynomial evaluations is exactly the same points which we had for the original code also. So the evaluation points will remain the same for the code and its dual. So the second thing which is useful for complete this talk is what is called trace of a field element. Okay, so I have a field. So this B is the base field. So I think from the paper they have two notations somehow. Okay, it's FQ, and this F is the extension field, which is FQ to the L. Okay, so F is an extension of B, and we are just defining a trace polynomial as trace of f over b of alpha is this sum, which is alpha plus alpha to the q, alpha to the q square, alpha to the q to the L minus 1, where L is this degree of the extension, right. So it's a very specific polynomial. It's called the trace polynomial. Okay. And what is good about this is that if you take trace of any element in F, it maps it to B. Okay. So it's a way of mapping elements in F to elements in the base field. Okay. And that is easy to see also. So like once you do some calculations in finite fields, it's clear. Trace maps the elements in the extension field to the elements in the base field. Okay. And the second important property is that trace is a bilinear operation, which means that if I take trace of B linear combinations of F elements, so which means that here alpha and beta are elements of F, but so they are, if you want to think about it, so the way I am always thinking is the elements in the extension field are vectors and the elements in the base field are scalars. Okay, and this is like a scalar combination of these alpha and beta. Okay, so this is b1 alpha plus b2 beta. The scalars are coming from the base field, the vectors are themselves are coming from the extension field, and it is linear. So the ones b1 and b2, they kind of factor out. Okay, and there is a converse too. It might feel that maybe you can get lot more bilinear functions, and maybe trace is one very restrictive kind of a function that we are looking at. So that already is taken care of by a fact that every bilinear function is a trace of something. Okay, so is equivalent to a trace map. Okay, so that way by looking at trace maps we are not losing anything, right? So what is a general operation that you would have done is that you would have multiplied a matrix and have vector of elements over B. So that's what we would have done. Okay, but instead of that we are looking at trace maps. Okay, all right. So another again important property of the trace. So this is like, so there is what's called, so I have a base field and an extension field, right? So that's what I have shown in the previous thing. Okay, I have a base field and extension field. Okay, so I can pick a basis in the extension field, right? For this particular extension anyway, right? So I can pick a basis which are linearly independent over B. So that I can pick, right? And here we are looking at what is called a trace dual basis. Okay, so U1 to UL is one basis, V1 to VL is another basis for the same extension. So the extension that we have is B over F. Okay, so for this I have U1 to UL as one basis and V1 to VL as another basis, right? And these two bases are said to be trace dual bases of each other if, okay, so if you pick trace of F over B of UI VI, so that will be non-zero, and rest everything else it will be 0. Okay, if I pick UI and VJ, where I is not equal to j, that trace will be equal to 0. So you have question? Okay. Okay. So why is, again, all these are very standard things in finite fields. Okay. Why are we interested in the trace dual basis? Is that I can pick an element, so it is like I can decompose an element in terms of the traces. Okay, so how am I doing this? So this is f of alpha star. Okay, so this f of alpha star is written as sum of L traces in the trace dual basis. So this is like as if projecting onto, you're taking a projection kind of and taking the corresponding component in the dual part. Okay, so if you know the Fourier transform, so that is, there is an analog of this, but the exact analog of what is happening in the Fourier transform is happening here in the trace dual basis. Okay, that you can decompose an element in terms of the traces, right? So that is this part. Okay, so now we want to use this decomposition to do the repair of f of alpha star. So assuming that alpha star is the indicator for the node which is erased, because node is identified by the evaluation points. They are all distinct, right? So we'll use this decomposition to be able to recover f of alpha star by somehow getting the, using this trace decomposition. Okay, but how directly? How will I get the traces on the right hand side? They also depend on f of alpha star, right? And f of alpha star is what was lost, and if that is what is there on the right hand side, it doesn't give me anything, right? So that is where the dual code will come into picture. Okay? So dual code property. Now what we are saying is that, so I have a Reed-Solomon code and I have a message polynomial of the dual code, right? And then this satisfies this property that, everything is orthogonal to the code words of this dual, right? In particular, this is true, right? Summation over alpha, f alpha, g alpha is equal to 0 because the evaluation points are the same for the code and the dual. So that's why you are getting f alpha and g alpha, okay? So f alpha, what I did not mention here is what are the degrees of these polynomials, but just keep in mind that degree of f is at most k minus 1 and the degree of g is at most n minus k minus 1, okay? And given that Reed-Solomon code, every polynomial is there, so as long as the degree condition is satisfied, it will be some message polynomial for that code, right? Okay, so this is the dual property. Okay, so now what we are going to do is that, so on this we are going to do two things. One, just keep the f alpha star g alpha star term on one side and push everything to the right hand side, okay? And second, do the trace on, take the trace on both sides, okay? So g, here, one choice that I have is I can pick the dual polynomials, the polynomials from the dual code I can pick, okay, somehow to get me good repair properties, okay. So that way it is not enough if I pick one polynomial, I have to pick a bunch of them. That's the reason why there is this gj, but what I have done is actually for gj, right, I've just, kept the terms of alpha star on the left, pushed everything to the right and applied trace on both sides. Okay, right?
Alpha 1 to alpha n and the same alpha 1 to alpha n used to construct the RS code.
Yes, that's right. Yeah. Yeah, so this A also is that only. A is like, the set of alpha 1 to alpha n. Right? Okay, so now we want to use this equation to somehow get, get to this equation, okay? Get to the trace decomposition, right? For that, it's again not clear, but what Guruswami-Wootters there, where the magic was to come up with a very nice set of polynomials for this gj, okay? So the next one, I'm just going to show you what is the choice of gj that they have made, okay? And why they have made that choice also, right? Okay. So the choice of gjx that they have made is, there is a trace sitting here too in that polynomial, but it's like this trace is for a reason which I'll explain later, okay? But don't assume that if I had to do something like this on the previous slide, I always have to pick gj's which consists of trace of some terms. No, that is not true, okay? But the polynomial that they picked was, so trace of uj times x minus alpha star divided by x minus alpha star. So this is the polynomial gj's that they have picked, okay? So how many polynomials did they pick? See here j is running from 1 to L. So they have picked L polynomials, right? Okay, and the only thing which is changing here is uj. Alpha star is the identity of the failed node, right? Okay, so gjx is, trace divided by whatever, x minus alpha star. So it has some properties. One is, if you just substitute alpha star, okay, so it may look as if, it is kind of maybe 0 by 0 form, but that is not true, because trace expansion, if you see, the first term itself was an alpha, okay. So it was alpha plus alpha to the q plus up to alpha to the q to the L minus 1, right. So that was the polynomial that you had for trace. I could just go back, but I am just writing it here also. So trace of alpha is nothing but alpha plus alpha to the q plus up to alpha to q to the L minus 1, right. So if I have trace of alpha divided by alpha, don't confuse with that alpha, this is just for, for argument, by alpha, right. So I'll just get 1 plus something, okay. So the 1 plus something terms, that plus something terms will vanish, but the 1 will remain, okay. So in particular, if you just do the calculation, it will be uj, okay. So that is evaluation of this gj at alpha star, okay. So what was the nice thing which happened is that we are somehow getting to the left hand side, okay, where you had gj of alpha star times f of alpha star. So there gj of alpha star is uj, but that is the term which is exactly in the trace decomposition, okay, which is trace of uj times f of alpha star. So that's what was there, right. So one property is matching, which is that you somehow have got something which looks like the right hand side of your trace decomposition, right. Okay. So what about, what happens to gj when you are evaluating at any other point which is not alpha star, right. So that is what is happening here, okay. So the left hand side you are evaluating at alpha star, the right hand side you are evaluating gj at all points except alpha star, okay. So which means that numerator denominator they will not cancel, right. But then if you substitute, right, it's trace of, here I substitute alpha, okay, and this whole thing and f of alpha, okay. So that is the term which was there in the previous slide, okay, the one on the right hand side, right. So inside gj you have substituted that with substituting alpha, and there is f of alpha, right. What did we do to bring it to this form is that, so whatever trace was sitting, because that is you saw that trace was a bilinear operation, so which means that if you have already taken the trace, you can pull it out of the trace. So otherwise what was happening was that this trace was sitting inside the other trace, okay, we just pulled it out, right. So this is the thing on the right. Why this thing on the right is interesting is that, so if you look at what are the things which are dependent on what the other nodes have to send me, okay. See, there are a set of n minus 1 nodes which are active in the system, only one node has failed, right. So the other n minus 1 nodes, they have their f of alpha, right. So whatever they are going to send should be a function of that f of alpha, correct. And whatever this part, okay, it's not dependent on f of alpha, it's just something which you can calculate later, right. So which means that what is the thing that each helper node, okay, the one which is helping should send is this trace of f alpha by f alpha, alpha minus alpha star. That trace is what it has to send. Every helper node has to send trace of its own function value divided by alpha minus alpha star, right. Okay. So how many symbols that it has to send? It has to send only one symbol, because trace is one B symbol, right. Okay. So and how did that magic happen? It is because these polynomials are such that when alpha equals alpha star, everything was uj. So if you look at the dimension of the span of these, evaluations over as as a vector space over B, if alpha equals alpha star, it is of dimension L. It is required because you want to recover that many symbols, okay. Whereas for everything else, which is alpha not equal to alpha star, okay, so the dimension of these things is just 1. Why is that? That is because gj of x has, it's like a scalar multiple of this one polynomial x minus alpha star, right? So even if I substituted alpha, as j was varying, it's only scalar multiples of this alpha minus alpha star. Scalar meaning b multiples of that alpha minus alpha star, right? So effectively, if you say the dimension of the span of these things as seen as a vector space over B is just 1, because there is one symbol which is 1 by alpha minus alpha star, one vector, and I just have scalar multiples of it, which means multiples of it taken from B. Okay. So what happened? It is like somehow from what you are downloading, okay, you are reducing that quite a bit, but still the other dimension you are still able to match. When alpha equals alpha star, you are getting the dimension that you want. Okay. So what is the total Guruswami-Wootters scheme is this figure. Okay. I have f of alpha star which is missing, and then I have all the other n minus 1 nodes. Each node is sending me trace of f of alpha 1 minus alpha star, and so on, all these traces. Okay. Then I am calculating the other traces using the equation, right? So which is trace of u1 up to ul f of alpha star, and then I get my f of alpha star, right? So now how many symbols are we downloading? Again, over the base field, one symbol is what we are downloading. So the download bandwidth for the scheme is n minus 1 total, whatever are the number of helper nodes. You know, if the size of B is q, log to q to the base 2 bits. Okay. And whenever this is less than k times alpha, or I mean k times L, right, you are at an advantage. Okay. So this scheme definitely better. So what did they do? They gave a very general framework to be able to repair and get advantage for repair. Okay. Yeah. Oh, sorry. Yeah. Yes. The first trace is like just coefficients which we know, because there is nothing which depends on the helper data in that, right? It's only uj which is the basis that I have picked initially, and alpha minus alpha star is the ones which again I know, right? So I know which trace is coming from which node, so I know what to apply, right? So which linear combination to take I know, right? Okay. So then what did they show is that, so for this there are some restrictions on the parameters for which you can do repair. Okay. I told as if it is the very general framework, but there are some restrictions. Okay. So one, n has to be less than or equal to q to the L, because my extension field itself is q to the L and I want distinct points of the Reed-Solomon code. Yes. Yes. So you should know which node has failed, and whatever the helper nodes send will be a function of which node has failed. Yes. But that is generally ignored. In all these settings, it is ignored, because all the time whenever helper nodes are helping, it is assumed that you are somehow conveying that, but that cost is never accounted for explicitly. Okay. So the first is n is less than or equal to q power L, so that is one. The second is, I said these are all gj of x, right? So the equation that I have used is as if gj of x were coming from the dual code, okay? But the dual code, so I know, and also I know what is the degree of gj of x the way I have written, okay? So all that we are saying here is, if they have to be from the dual code, the degree of the gj of x which is coming from that equation, okay, should be less than the degree of the polynomials in gjx, I mean in the dual code. That will give me this condition, that n minus k should be greater than or equal to q to the L minus 1. And what they also have shown is that this repair bandwidth, whatever you get, that n minus 1 log q to the base 2, so that is optimal if, okay, both these are equal. Okay, which is n equals q to the L, and n minus k equals q to the L minus 1. So for both of those equalities, they have a nice counting argument which shows that this download bandwidth is optimal. Okay. For anything else, we don't know. Any question? Sorry. Okay. So is this clear till now? Why do you say that? I think so. N minus k has to be very large. N minus k is quite large here. Right? Okay. So then what is the next scheme which, let's say, improves upon this in terms of, let's say, even generalizing the previous scheme? Okay. So how it is done is that, so instead of the gj of x which they have taken, okay, so they are going to take different gj of x's. Okay. And what is the rationale behind it, or what is the rationale of generalization is that, so there they use trace polynomial divided by something. This here also is going to be the same form, but trace is, as I said, it has all those nice properties, but it belongs to a class of polynomials called linearized polynomials. Okay. So the linearized polynomial, a general form, okay, I am sorry about the typo here, I think I did not check it, sorry. Yeah, but it is this I equals 0 should be below. So I equals 0 to d, some degree, okay, li x to the q to the I. Okay. So linearized polynomial is a polynomial which has only q powers. Okay, it does not have any other powers. In particular, you can see trace has this property. So trace is a linearized polynomial. Okay. And why it's called linearized polynomial? Exactly for the same reason that, I mean, what trace was giving. Trace is bilinear. A linearized polynomial, I mean, if you evaluate that also, it will be like, yeah, it is bilinear. Okay. So exactly the same thing. Okay. But this gives us much more choices for your gj of x. Okay. The trace was one particular choice. So this trace I am talking in the context of trace which was there in gj of x. There was a trace framework before, that will stay as it is. Okay. All that changes in this scheme is what is gj of x. Okay. And what is gj of x? It is going to be picked as if it is a linearized polynomial. Okay. And linearized polynomial has another characterization also. Any linearized polynomial, okay, if you see, the zeros of that actually form a subspace of your extension field. Okay. So somehow it is like, if some zeros are there, even those bilinear combinations are zeros of such a polynomial. So the zeros is a subspace of your extension field. Okay. So the other way to look at it is that I can construct a linearized polynomial by picking the subspace of my extension field, right? And that's what is done here. Okay. So what is done is W is a subspace of some dimension S over B. So it is a subspace of your extension field, but it is a B subspace, right? So I mean a B vector space. And the way you're going to form this polynomial is by just, you know, as if it were zeros. So every element in this W is a zero of this polynomial, right? What is shown in finite field theory is that this LW of x exactly has this form, okay, which means that it will have only q powers, it will not have in between powers. Okay. So if you see now, the gj of x which is picked in this is exactly LW of uj of this thing. Instead of trace, it is a general linearized polynomial. Okay. And the guarantee that you can give somehow is that, again, when you are actually evaluating at alpha equals alpha star, it will not be exactly uj plus, but some, you know, multiple of uj. Okay. Maybe minus 1 power something times uj or something like that. Okay. But effectively for our purposes it is uj's. Okay. For the rank purposes it is, when you evaluate at alpha star, it is going to be dimension L, which is good. That's what we want. Okay. So the other part, earlier it was 1. Okay. So earlier when you looked at that, it was 1. Okay. But now it is like the dimension is at most L minus S. Okay. And the way to think about it, I am only just giving an intuitive argument why that is true, is because this LW is going to vanish on all the elements in your subspace. Okay. And that's of dimension S, right? Okay. So if you have a map LW, right, it has a range, it has a kernel, right? So the kernel is at least of dimension S, right? So we can argue that this will exactly be not equal to L minus S, but it will be less than, okay, because this is somehow, you can say that it is kind of range of LWs in some sense. Okay. So using that argument, you know that L is, for alpha equals alpha star, it is this, but for alpha not equal to alpha star, it is at most L minus S. So that is the direction also that we want, because we want some guarantee on the repair bandwidth. Okay. Why is it that we are looking at the dimension? Is because I might have a whole set of symbols, but I am only interested in sending some things which are linearly independent. Okay. So as vectors, I'll have some things, right? I may have a lot more of them. I mean, if I substitute, I'll just still get so many of them. I'm only interested in sending the linearly independent ones. Other ones I can calculate at the node that I'm recovering as well, right? So just to keep track of that, which are the linearly independent symbols that I have to send, the dimension will come into picture. Okay. So how did we improve on the parameters in this is that the constraint on the parameters, again, n is less than or equal to q to the L, that is the points that where we are evaluating, and I have L polynomials because here even in this you have the uj, and uj is u1 to ul. Okay, fine. So but then n minus k is greater than or equal to q minus s, q to the s, because LW itself as a polynomial, right? So the LW of whatever is sitting in the numerator, so that I think that is of because it has, you know, all the roots in W, and the number of elements in W is q to the s, right? So the LW will be a polynomial of degree q to the s. Okay, and there is a minus 1, but that minus 1 will get cancelled with another minus 1 in the next one, so that's okay. So all that you get is n minus k is greater than or equal to q to the s. What was the last time that we had? What was the thing? It was n minus k greater than or equal to q to the L minus 1. Okay. So L minus 1 is the maximum value which S can take. S gives you the flexibility, right? Depending on which subspace I mean. And I don't know, I don't think, or maybe because they don't, at least for these purposes, the actual which dimension, which subspace you are picking may not matter. Maybe it does, but you can't generalize and say that this is the best subspace to pick. You have to check what is its dimension and so on, right? But you get the guarantee, and what they have shown in this paper also, which is by Huang, Dao and Milankovitch, the repair bandwidth is optimal again if n equals q power L, like in the previous case, and n minus k equals q to the s. Okay. So for these two values, the repair bandwidth is optimal. So from the previous thing, what is the repair bandwidth? It is n minus 1 into L minus s, right? Because this is the dimension. For each node, that is the dimension, and I have n minus 1 of them. So it is n minus 1 into L minus s, right? So that is the repair bandwidth for this key, and that is optimal if you pick these parameters. Okay, is it clear? Okay, so from now on, it's like, because I have very less time, at least I think I did cover what I wanted to in as much detail as possible. The rest, there are so many details, but I will just skim through. Okay.
You mentioned vectorization and
Yeah.
physics.
Yeah.
Can you connect it to what you just mentioned?
So see, the thing is here, when we are sending traces, right? and I said it's a bilinear map, right? So what it means is that, so when I say I am writing trace of f over b of this f of alpha divided by alpha minus alpha star, so this is what I'm doing, right? So this is like as if I'm having this symbol and I am doing a bilinear map. So this, if I view it as a vector over b, okay, the trace of this will be a linear combination of these symbols. That's what is happening, right? So that is how the vectorization is working. Okay, all right. So, so what we have done, I will just tell you. So there are another class of codes which I said called locally repairable codes, and one famous class in that are called Tamo-Barg codes. They are optimal, okay. So but then I will not tell you a whole lot, but all that I can say is that they are polynomial codes, okay. So they are polynomial codes, and here if you see I have just denoted some partitions. So it's a code in which there are component Reed-Solomon codes sitting there, okay, right? So what did we say in LRC? It is like we are actually minimizing the number of nodes that we are contacting, okay. How is that coming? That is coming from this partition, okay. The way it works is that, is that when something is lost, I'm not going to the other nodes in the partition. I'm only looking at this and connecting somehow to our helper nodes and recovering the value at that. Okay, that's what is happening. And in particular, the Tamo-Barg codes are one polynomial codes. Second, each chunk, if you look at independently, each one is a Reed-Solomon code by itself. Okay. So the question that we asked, we had a paper. So what we were asking is that, yes, here, within this Reed-Solomon code, okay, can you use the Reed-Solomon repair kind of techniques to even further reduce the bandwidth? Because LRC is a different paradigm, okay, where you are only saying this many nodes I will contact, but our nodes in that, but we are actually downloading everything from there. But even within this Reed-Solomon code, it's only one symbol which has failed, right? So which means that can you use the Reed-Solomon code trick of repairing Reed-Solomon codes within the local code of this Tamo-Barg code. Okay. So we have given two techniques to do that. So one is what is called based on cosets, and the other is some nice field extensions and all that. But both the tricks are somehow generalizing the existing Reed-Solomon framework only. Okay. So the one based on cosets is kind of generalizing the Dow-Milankovitch scheme which I had shown. So you have to kind of pick some coset and then take a subspace and then kind of make your G polynomials and all that. Okay. So that is one scheme that we had. The second scheme, which I did not talk about even in the Reed-Solomon code context, is based on a work by Tamo-Barg. Okay. But all that I can perhaps show you is that there's a catchy. So what question people were asking is that, so in regenerating codes there is a fundamental limit. Okay. So by vectorization there is a fundamental limit to what is the minimum repair bandwidth that I want. Okay. And the ones which achieve that are called MSR codes, which is minimum storage regenerating codes. Okay. So what Tamo-Barg somehow have shown, or their construction shows, is that even Reed-Solomon codes, you can make them MSR codes. Okay. Because both the previous bandwidths that we got, n-1 or n-1 into L minus S, right? Both those are very, very away from this cut set bound, which is promised by the vectorization. Okay. So if we were not, if we are just not vectorizing a Reed-Solomon code versus, designing a vector code from scratch, we know how to achieve this number. Okay. What Tamo-Barg and Barg have shown is that even this you can achieve with Reed-Solomon codes also, but, okay, but you have to design your fields very carefully, the points very carefully, okay. And I can tell you what is the catch of their construction. So the catch of their construction is, there is a, so in finite fields you can draw various towers, okay. So which means that extension field, based on what is the degree of the extension, there will be various subfields in an extension field, okay. So they are kind of constructing some tower, but what is the catch is that somehow when you want to achieve the cut set bound, okay, it is like for every node you have to take the trace over a different subfield. So earlier what we were doing was that we are taking trace for all the nodes on the same subfield, which is B, right? So here the tower structure is that there, first of all, there are n different subfields, okay, and for every node there is some unique subfield associated with it, which is at F1, F2, Fn, okay, and for repairing node 1 you are going to take the trace over that F1, okay. So the highest field where the code is sitting is K. There is a reason why this particular thing is there, but that's not very important right now at least. So, but the K, if you, for repairing node 1 you will take the trace over F1, for repairing node 2 you will take the trace over F2, and so on, okay. And they show that this kind of thing is necessary also in some sense, okay. The reason is because they somehow tie it to the fact that there is a unique subfield of a certain size in an extension field, okay, and that, and if we don't do this, somehow the repair cannot happen at the cut set bound, okay. So the repairing, if you want it at the cut set bound, okay, if you don't do this, you will end up in a situation where you will need two subfields of the same size, but that doesn't exist, okay. So which means that you have to do this repair or traces over different subfields, okay. But the thing is, again, the math is all nice. The reason the scheme is not, yeah, at least as practical as MSR codes is because this requires a subpacketization, that L, Q to the L, whatever we have, which is doubly exponential in K. So this requires, because it is like, I require at least an extension field which is product of first n prime numbers or something like that, okay, which is like n power n kind of thing, okay. So what we do is we do some such thing for Tamo-Barg codes also, but there is a trick involved there. So it is not immediate what has to be done, but I will not talk about that. I'll stop here. Yeah, that is also called local regeneration. Yeah, so that's why these codes are kind of codes with local regeneration, but assuming the scalar code is a Tamo-Barg code, yes, you're right. Yeah.
Any more questions?
Thank you. Okay, thanks. Yeah, sure. Thanks for coming.